Okay, great. I really have the feeling that I have now the best transition to the next presentation, since Holger Becker already talked about life cycles. And I'm pretty sure that our next guest, or not really guest, but our boss, Frank Bartels, is going to take that to the next step. He's taking a look back at his more than 30 years of experience in microfluidics. And he's going to show us what the very first microfluidic application was and just how we got here, basically. So, Dr. Bartels, the stage is yours.
Okay, thanks, Alicia. And yes, I have to really thank to Holger that he was willing to be the first presenter here, because definitely he has to do a very, very important job when he goes to the parliament. I believe he really showed us, okay, how deep his knowledge is in all these funding problems for R&D, and that he's really the right person, okay, to bring it to the parliament. So thanks for that. Holger and I were really together since more than nearly 30 years, and he started with some, let's say, historic considerations and how to bring, let's say, technology to market, and that's a little bit what I will try to strengthen a little bit more in my presentation. Because okay, I followed with the same process with him, and okay, that's Bartels Mikrotechnik, because I myself, I'm now 25 years or 27 years of microfluidic expertise in Bartels Mikrotechnik. Before I was in a company, Microclouds, maybe that some of the older people, okay, know it. And from that time, I had some good understanding and quite old OPA-like, so grandpa-like understanding of microfluidics. This was the first, let's say, microfluidics elements. I was contacted to, I believe everybody knows the HP inkjet printer from 1988. It was a real wonder. Suddenly we had colored droplets forming a picture, and not this former printers. This was a real topic, and it was 300 dots per inch. Okay, what is droplets per inch, which means there's a nozzle distance of 85 micrometers. So this was in a very early stage, a really nice, and I believe later on not really recognized fluidic system. Actually, okay, 20 micrometer, the actual status is really, really nice. And every technology will move in a lifetime circle. And sometimes it goes quickly. In microfluidics, okay, are in industrial. My example was with a printer, was more in the industrial area, but we focus today to the life science topics, and we know diagnostic, pharma, medical. Okay, where is the position now, and how we can separate this? It was quite clear that Holger, okay, you may come up with the same starting point of microfluidics than I pick up again the Journal of Chromatography A, and Mr. Manz made the first, let's say, one of the first fluidic chips to measure some things, some elements in the channel electrophoretic. And so I have to say thanks to Mr. Manz. I believe he was the inventor of this mutas label. If I'm wrong, okay, there may maybe a lot of experts who know these things better, and they may correct me. Thanks to Mr. Manz. And now I have to tell a little bit of my personal experience. And this was during my time at Microclouds at that time. And I visited in the company Biosite in San Diego. And there were two people, Kim Brickenstaff and Kenneth Büchler, who invented, let's say, a fluidic diagnostic system for troponin T. Troponin T, very nice and important topic. If you have a heart attack, you can measure whether it is a heart attack or something else. So this was a really important topic. And to be honest, because I had a heart attack some years before, I had to use it, unfortunately, several times. And at that time, 94, I saw exactly this very nice fluidic structure. So a lot of capillary flow, inside, and there is an element which sucks in the liquid. All these antibody and topics were incorporated there, and then there were a device developed, and the application of the technology started in 1990. I believe the application was 94 when Biocide at that time presented this as a very nice application. Product start was 2000, and today it's common. So as always, there's always, let's say, a lifetime, a circle indicator. So let's have some thoughts to innovation processes in general. Every product has a lifetime. I believe that's what Holger just mentioned before. We have, let's say, a first phase where we have a quick design change, definitely 1990 to 94. A lot of improvements were done, no standards, low product volume. And then we come up, let's say, the design starts to become more stable. The product innovation slow down, and there is then the transfer to something which is dominant and which allows us, let's say, to create, let's say, specific and realistic production cycles. And then the third phase, okay, I believe Holger mentioned it before, cost competition. That's the key element, okay. Only price makes that. But I wanted to state that these general process, okay, in life cycles, I believe we are in phase 1 and starting phase 2, and the really phase 3, or maybe with the COVID test, this was mentioned by Holger before. This may be something where we are really, really at the late end, but in a lot of important elements, okay, we are in phase 2. And this I want to summarize a little bit, and everybody who knows me that I'm a real fan of the Gartner hype cycle. If somebody don't know it up to now, that's the idea that we will have a starting period, technology trigger, where the first ideas come up, and then a peak of inflated expectations. Okay, this is the position where, let's say, the government normally invests in it. And then everybody is excited, wow, okay, the word will come. I remember really careful to the year 2000, where everybody dreamed for the lab on the chip. So having one droplet of blood on your health status, okay, is immediately available. This was the dream, and a correct dream. That's the nice situation. But it really took some time. And then there is the thought of this disillusionment will come up. We know these processes quite well. We go through it, and Holger and Becker, and I believe, I'm sure a lot of other companies know it quite well. You have to get away from all these pitfalls you are falling into the processes. You have to wait that maybe the production process is ready, or maybe getting a top layer on top of a micro channel, okay, without destroying everything what you have implemented internally. All these need to be solved, and later on, then we have the slope of enlightenment. And in order to understand our actual position and to understand, okay, in which direction it will go, we have to look a little bit more in details about the different elements of microfluidics. I have not found a specific Gartner hype cycle, especially for life science or microfluidic. And so maybe that somebody knows one, that would be nice that you tell me 10 minutes. And so I made it a little bit myself. And start to find a little bit historic timeline. Okay, on the Elvis website, I saw these very nice lifetime. We start with Hagen-Poisson. Okay, fluidics is something in the 94. There's the lab-on-chip elements. This was the first lab-on-chip elements. And so there are a lot of different, let's say, keywords were internally. So capillary electrophoresis, diagnostic chip, lab-on-chip, organ-on-chip. These are the elements which are in that, and historic timeline can only be done, let's see, for the different elements inside. And it was really a topic here. A capillary electrophoresis, I tried to use the cycle curve in order to put some, let's say, dates in it. Started 1990, everybody was excited in 96. And then, okay, some disillusion come up. And today, I believe products behind that and are in the market, so I put 2005 to it. But that's definitely not the case for the diagnostic chip, because diagnostic chip means, okay, there is more information in it. You have to solve, let's say, more problems to do it, but it's even a fast track. I said, okay, the peak of inflated expectations was 2000, and the disillusionment came quite quickly. Okay, it really took, what was a fast process to understand, oops, the idea is nice, but the problems which must be solved are tremendous. And what you normally need, you have to, to combine different technologies and all the money which was spent at that time in funding and in universities and companies to solve the problems, I believe were necessary. When I go to the next topic, let's say lab on chip. So this is even more complex. I believe a real lab on the chip, that's something which we actually have. Holger showed, I believe, a very nice example where you have a complex system inside, and he mentioned the photonic sensor, which is now incorporated. This is something which really, okay, shows a more mature situation. And again, with the lab on chip 2000, I believe it was really 2000. At that time, we had, let's say, a laser structuring system, and it was every week a new startup came to us and told us about test systems which will have a huge market, and they come up with all the same numbers. Maybe somebody gave the number to the world, but every startup every week come up with another technology to detect the antibody reaction, and it was quite clear it will not be so simple. And so these drop down, let's say, the disillusionment will come. I believe what we have now is droplet generation. Again, that's something, the idea come up, wonderful idea, we can generate with the right chips. You need the technology to have the right chips, you need the correct flow rate in the different channels, all this is necessary. And it took some time to come up with, let's say, some systems to solve that. But a real product, droplet generation, maybe a cell which is in a container, which is in another liquid, again, the transporting, there is something on the way. There will be some volume application. Which one, I do not know exactly. That's something which the future will show us. Again, if somebody knows that there's, let's say, a very key application which is really in high volume, it would be nice that somebody tell me this. Organ on chip, again, this is okay. The next a wonderful idea to have. I've seen a lung, some cells which mimic the function of lung, and so you can test all the pharmacy, let's say, not on human body, or on some animal bodies. You can test it just in a test system in the lab. But then the organ, okay, must be organized in a way which is close to what happens inside of the body. So, and maybe the idea to have a replacement of one of our, let's say, failed and damaged parts of our body. This is a very wonderful idea, but again, this job is very, very complex, and I believe that's something which will happen. So the future of all these elements and the microfluidic is really, really interesting, nice, important for the society. So that's something which is a topic. And what I wanted to tell us that when we are discussing history of microfluidics, then we really have to take care, okay, which element inside, okay, we are actually talking about. Okay, we can make the same idea in a little bit different way. Organ on chip, okay, that's maybe in the phase that first disillusionment come up. Diagnostic on chip is in the market, okay, maybe that's the way how to mimic a little bit Gartner website. And what is the actual height? So I do not know, because I'm during the last years more in the, let's say, production volume, maybe in more mature phases. So what will be the next actual height in physics? So let's see. What enables a successful journey through all this? Because that's what we are all a little bit part of, maybe in the technology area, or maybe in the production area, or maybe in the market analysis area. What enables a successful journey? This is first an attractive market, and second, a very easy access to necessary or supporting other elements. And this can be technologies, production process, material, whatever. So, but you need an easy access to come through all these processes quite quickly and be successful in the end with high volume. And so I looked a little bit again. As I said, I'm a fan of Gartner curve. I looked again to that. Let's back to MEMS elements and microelectronics. We have a very nice curve. I will not go through it in detail. I believe it's without doubt that we are in the plateau of productivity. When I look to my smartphone and see that there are, let's say, 3 orientational motion sensors with 14-bit resolution, including magnetic sensors with 12-bit resolution, and all this is for $1.50. This is a wonderful situation. And this is available now, and the successful of all these MEMS elements and microelectronics. We have a lot of sensors available, all that. And then we go to microfluidics. Okay, we come up later, and we have our own curve. As I said, can be complex for the different applications in microfluidics. But the big advantage is that we can take now advantage from the established processes and products from the MEMS world, because this speeds up. So what we need is always a simple and access to what is available and which support us. Now I can, or the people in the can generate, let's say, a diagnostic signal, and there's no need, let's say, to make all the electronic development, maybe, and like in Bluetooth chip or that, because this is now easy available. And let's go to biotechnology. A lot of the, let's say, earlier applications for microfluidics are in biotechnology. And like organ on chip, this is something which will require a lot of additional work. And the people sitting there doing their very complex technology, they know everything about the biology, but does they know about fluidics everything? Sometimes yes, often no. And that's what we have learned. What we should do, we should enable, let's say, the biotechnology to take advantage from what is established in all the microfluidic world. And so, as I said, what is necessary to have a successful journey through the hype cycle, the attractive market, and the easy access, and the world of biotechnology, gene technology, cells, organ, will need an easy access to the microfluidic functionalities and to enable the realization of this enormous potential. And that's the job now. And when I look back to what we have done the last, let's say, 5 or 8 years, is to get rid of all these phone calls for people who said, okay, you have a wonderful component, but okay, I'm not able to bring all these topics easy together, that it will really run. So that's the job now. And that's what my message. Have fun today with us. And I have to say sorry for wasting your time with some, in principle, trivial messages, because that you need other technologies, supporting elements. I believe that is nearly trivial, but we have to have it in mind in order to get an idea in which direction, let's say, the next elements of microfluidics will go. Thanks.
Thank you very much, Mr. Bartels. we had some comments during your presentation. I'll get them up right now. Okay. I would have counted digital PCR to be sort of a product method of droplet generation, but of course it is not a completely new technology. That was also agreed on from Mr. Zenger.
Yeah, that's completely right, because droplet generation, okay, you can create a droplet without, let's say, having microchannels, and but in order to bring them in, let's say, an analytical or maybe, let's say, cell organization or this, then you need more control than just from the droplet. To create a droplet requires a lot of understanding and control of the surface tension and flow rates. You need a lot of control of all these elements. So it's completely right. Okay, to create a droplet, okay, everybody can do this at home in the bathroom.
Maybe just one more quick question that hasn't. Oh, wait, there just came up something. Thanks, Mr. Bartels, for the nice talks. I also agree that the entire life science and the biomedical diagnostics will be the markets of the future. Are there already any plans to directly tackle them?
Okay, from our company, it's quite clear that we will not address these elements by ourselves. So my hope is that with the easy access to, let's say, simple and handleable elements, okay, the people who make all these biotechnology, okay, and more of them, okay, and will go into that direction. So this is not the job of the company Bartels Mikrotechnik itself. Our job is to make, let's say, the access simpler, maybe to generate and to bring in all the experiences which we have accumulated over the last 20 years, let's say, into processes. I'm now becoming a startup of software, because how to handle, let's say, a small gas bubble in a liquid channel, okay, is a tricky topic. And then simple elements, okay, go a little bit forward, backwards, let's say, get rid of the bubble by getting it out with a different syringe or whatever. Very nice, but it's not so easy to bring all these experiences, let's say, to somebody who's really interested in biology. And so we are now on the way and start to bring these experiences in a software which handles the different components in a way that solves this problem. This is, I believe, the way how Bartels Mikrotechnik will go into these markets and these jobs.
Okay, thank you very much, Mr. Bartels.
Thanks.